Hi class, we're here for the last section of chapter 5, which is applications of the determinant. So in the last two sections, we talked about what the determinant was, different ways of finding it, and a few of the properties of the determinant. So today we're going to, again, talk about a couple of properties, but mostly what it is that we can use the determinant for application-wise. We've found a couple of uses for it already. But they were more so for things that we're interested in from an algebraic standpoint, like linear independence, is there an inverse, things like that. So today we're going to actually talk about using the determinant to figure out actual stuff, right? So one of the main uses that we have for the determinant is to find a solution to a system of equations. So just to recap, as of right now, we have several ways of finding a solution to a system of equations. You have your standard algebraic methods, which is the elimination method or the substitution method, where you're keeping things in terms of x, y's, and z's and substituting things, or trying to eliminate a coefficient by getting the coefficients to match and then adding the equations together or subtracting them, right? That's the way that you learned a long time ago. Coming into this class, I told you guys to forget about that and to embrace the Gauss-Jordan elimination method, right? So that's our third method, was the first new method we learned in this class, was Gauss-Jordan. From Gauss-Jordan, we also learned that we can use inverses to solve. And we also learned that we can use, briefly how to use LU decompositions, or the LU factorization to solve a system, which we use using basically matrix algebra and Gauss-Jordan methods. And then today we're going to talk about how to use it how to solve a system by using determinants. I'm sure I've probably forgot a method or two because we've been talking about systems a lot. So let's get into this, okay? So using determinants, you might have actually seen this method before. It's often taught in a pre-calculus course. And it's a method called Cramer's rule, okay? So if you've seen Cramer's rule before, then you're ahead of the curve, and you know, this will just be a review for you. For some of us, this will be brand new or a refresher. So the way that this method is described is that if we have a square matrix with real values, okay, that is invertible, so it's a non-singular matrix, meaning that the determinant is not zero, then the components of the unique system, or the solution to the unique system, ax equals b, are given by x sub I, so each different x sub I, x1, x2, x3, etc., up to xn, are given to you by the determinant of a sub I divided by the determinant of a, right? So really, in order to solve your system, you're just finding a bunch of determinants. Now, the only thing that's going to be different is this a sub I. What a sub I is means that you are replacing the ith column of A with this B vector, and then finding the determinant, okay? And that's how you find the x sub ith term in your solution. So A sub I is the matrix A, but with the ith column of A replaced by B. So for x1, you're going to take your matrix A and you're going to replace column 1 with this B column, okay, this B vector. To find x5, if you have a 5 by 5 or something larger, to find the fifth term, the fifth solution term, you replace the fifth column with B. Okay, so all you're doing is replacing, you're going down each column and you're replacing each column with B one at a time, and each time you're finding the determinant, and that's your numerator, and then you're dividing by the determinant of the original matrix A. Now, obviously, you're going to find a lot of rational numbers here. Always fully simplify them, right? So, for instance, if you come out for like your x2 term is 20 over 40 for some reason, don't tell me your answer is 20 over 40. You reduce it down to 1/2, right? Same thing if it comes out to be 40 over 20. You reduce it down to 2. I will 100% mark you down for not simplifying your fractional values to the simplest term. Okay. I also do not want decimals. simplify it all the way down to simplest terms. Do not give me decimal values. I will mark you down for decimal values as well, as you have likely seen in this class already. Okay. So, example. Let's say we solve this simple 2x2 system where it equals 3 over 5 using Cramer's rule. So again, if I gave this to you at the beginning of the semester and before you had any linear algebra tools available to you, you would have probably multiplied this thing by 2 to get the coefficients to match up, added them together to cancel out the x2's, or you would have solved for this x2 and then plugged it into this equation, right? So those are the two methods that you learned before you even went into this class, right? The first method you learned in this class was the reduced row echelon form to simplify this system down into a triangular matrix, or using Gauss-Jordan so that you have x1 and x2 fully solved for. So we spent a lot of time on that. We have also talked about how to find the inverse of this and just use the inverse. As I said, that's my preferred method for solving a system, especially if it's square, or it only works when it's square. But finding the inverse and then using the inverse matrix to solve this. We've also talked about the LU decomposition, or the LU factorization, where you find an L matrix, you build an L matrix and a U matrix at the same time, and then you can use that to solve this. We saw that it's kind of time consuming and is really only useful when you have several different B vectors that you want to use, right? So again, now we're going to be using this new method that we're calling Cramer's rule, or that is called Cramer's rule. Okay. So first things first, let's turn this into a matrix equation. Okay. This is the A, this is the X equals B. Okay. Now again, my preferred method, especially for 2x2, is really easy to find the inverse matrix and just multiply that times that, but that's not what we're doing here. So what I'm going to do is I first need to find the determinant of this, which is this diagonal times this diagonal, right? It's subtracted from this diagonal. So that's 7 minus a negative 6. So that should give me 13 as the determinant. Okay, so that'll be my denominator for all of my solutions, is 13. So the next thing that I want to do is I want to start solving this A sub i's. So we only have x1 and x2, so I should only come up with 2 solutions here, right? An x1 and an x2. So my first matrix, I'm going to replace 7, 3 with 3, 5 and find the determinant. So that's the determinant of A sub 1. Okay. First column replaced with my B matrix. So that's going to give me 3 plus 10, or 13. So x1 is going to be 13 over 13, right? This is my numerator. This is my denominator. I have 13 over 13, or equivalently 1, right? I'm going to find the determinant of A2. So I'm replacing negative 2, 1 with 3, 5. And then I'm doing my, cross multiplication for the determinant, right? So that's going to be 35 minus 9, which is 26. So x2 is 26 over 13, which is equivalent to 2. Therefore, my solution is 1, 2. Okay, it's actually very simple, very straightforward. It works really fast also with a 3x3 system. You're just doing that 3x3 multiplication method for the determinants to find your 3 determinants. I guess 4 because you got to find A also, right? So 2x2 is very fast. 4x4s or 3x3s are pretty fast too. 4x4s, you might need to mix up your methods. As we saw before, you can mix in your cofactor expansion with the 3x3 multiplication rule. You can reduce down to a triangular matrix using your row operations, and then use that method where you're multiplying the diagonal but keeping track of your row operations. That might be faster sometimes than trying to do 3 or 4 different sets of cofactor expansions, or depending on what your values are, right? So we can also use the determinant to find A inverse. Okay, so in order to find the determinant using in order to find A inverse using the determinant, we're going to use cofactors. Okay, so we're going to do several cofactor expansions. We're actually going to find the cofactor for every position of the matrix. Okay, so this is a little bit different than the cofactor expansion because we're finding the cofactor. We are not multiplying the cofactor times the entry in the matrix. So don't make that mistake. It's easy to make because you're used to doing something else, right? So this is called the adjoint method. Okay, the adjoint method. A inverse is 1 over the determinant of A times the adjoint of A. So what we're going to do is we're going to talk about finding the adjoint because the determinant of A we know how to find already. Okay, so the adjoint of A is the cofactor matrix transposed. Okay, so you find the cofactor matrix and then we transpose it. The cofactor matrix is the cofactor entries of each of the entries of A. Okay, so to create C, basically what we do is we find the cofactor of each entry of A, as I've said before. So remember that cofactors are this companion matrix entry times the minor. Okay, so what we were doing before was we were taking these values and then we're multiplying it times the entry Aij that we were at. So here we're doing all of the work except for multiplying it times the Aij term. Okay, so remember the minor is the submatrix, the determinant of the submatrix that you find when you block out the rows and the columns of whatever entry you're at, right? So we're doing that, but we're not multiplying times the entry. So let's just do an example. Once you have an example, it's easier to see. Okay, find A inverse using the adjoint for A. Okay, so here we're having a lower triangular matrix. That makes it easy for us to find the determinant. Obviously, the determinant is 12, right? 2 times 1 times 6, because that's how diagonal and triangular matrices work. Okay, so the determinant of A is 12. So that means that once we find the adjoint, we will divide every entry by 12, because 1 over the determinant of A times the adjoint matrix. Okay, so we're going to find the cofactors for each entry. Okay, the cofactors for each entry. Remember, this alternates in the sign. So it goes plus, minus, plus, minus, plus, minus, plus, minus, plus. Right? Those are the signs for the cofactor terms. So for cofactor 1, 1, okay, I'm going to block out this entry, these rows, I'm going to block out these columns, and I'm going to find the determinant of this submatrix. That'll be my minor, right? So I'm going to find the determinant here, which is obviously very easy, 6, right? 6 minus nothing. And that will multiply times the sign for this position, which is the negative 1 to the power of I plus j, which is 1 plus 1 or 2. So this ends up being positive, right? Positive, negative, positive. So this is going to be positive, just this subdeterminant, which ends up being 6. Okay. For the next entry, C 1, 2, this will be multiplied times a negative, whatever value I get. Because remember, this sign here, right? We can always look at the companion matrix, plus, minus, plus. So whatever I get, I will change the sign. This one I didn't have to because it was in a plus position. Here it will be in a negative position, so I block out this row, this column, and my submatrix is 8, 0, negative 5, 6. Okay, and it'll be multiplied by a negative because of this term, right? Because of the companion matrix, plus, minus, plus. So here I'm going to have 48 minus nothing, so this will end up being negative 48 because I'm multiplying by negative at the end here. Okay, same thing here. I block off this row, this column, it'll be positive, and I'm going to get 24 minus a minus 5, or positive 29, right? So these 3 entries are the first 3 entries for my cofactor matrix. Okay, those are the first 3 entries for my cofactor matrix. So I'm going to do the same thing here. Block out this column, this row. The submatrix is 0, 0, 3, 6, and it's in the negative position. That gives me 0. Okay, I'm going to go to the next one. This is in a positive position. Okay, delete this, delete this. I have 2, 0, negative 5, and 6. Okay, it's in a positive position, so I don't have to multiply it times the negative. This gives me 12. Okay, I block out this one right here, so this row, this column, it's in the negative position, and then the submatrix is 2, 0, negative 5, 3. Okay, it's negative 2, 0, negative 5, 3. That just gives me a value of 6. Okay, and then I make it negative. And then I come to the bottom row. I'm going to do the same thing. So why don't we pause it right now and you do these last 3 very quickly. And again, just make sure that you get the same thing that I get. So let's pause it in 3, 2, and 1. Okay, so welcome back. Hopefully you guys took the time to go ahead and do this bottom row yourself. And let's just compare our answers. So again, I'm blocking off this one, taking out this column, this row. This is my submatrix. It's in the positive position. And I get out 0 anyways because it's 0 times 0 minus basically 0. So it doesn't even matter. Okay, it's going to be 0 anyways. Same thing here for the next one. This is in the negative position. I'm going to take out this row, this column. I got 2 and 0, 8 and 0. So it doesn't matter that it's negative. It's going to give me a negative value anyways. Then I have my last one. It's in the positive position. Okay, and this is the submatrix right here, this 2, 0, 8, 1, which leaves me with just 2. Okay, so now I have all of my entries in their proper positions, which is why I did the top 3 and then I came down, and then I did the next 3 and then I came down and I did the next 3, right? Although I am limited to space, this is how I would have done it in a regular class on the board. I would have still done it in this order because now they're all in their proper position. You can see what the matrix will be. 6, 0, 0, negative 48, 12, 0, 29, negative 6, 2. That's my C matrix. They're all in the right position. But notice that the adjoint of A is the transpose of that. So on this next screen, I will write this matrix, the 6, 0, 0, negative 48, 12, 0, 29, negative 6, 2. And then I will transpose it. Okay, so I'll flip it across the diagonal. And I will multiply it by 1 over the determinant of the original matrix, which was 12. So I'll divide all of these values by 12, and I'll transpose them. Okay, so this is my matrix for C, my companion matrix. So that means that adjoint of A is C transpose. So I transpose this matrix, the diagonal stays the same. Okay, so that's adjoint of A. And A inverse is 1 over the determinant of A of adjoint of A. So I'm going to take this matrix and divide it by the determinant of A, which is 12. Okay, so multiply 112 across everything. If you notice, everything here simplifies nicely with 12 except for 29. So simplify your values. Do not leave me 6 over 12 in this position. Do not leave me 12 over 12 in this position. Make sure you simplify your fractions. Okay, I will mark off points for not simplifying fractions at this level, right? This is a linear algebra course. Definitely reduce all of your terms into their simplest form and leave them exact. This is how I want them. I do not want decimals either. Okay, so this is A inverse. Okay, now it may seem like it takes a little bit of work, but so does everything else in this class. And you can actually do this really, really quickly if you're good at determinants at this point, which hopefully you guys are. But you know, there is work involved, obviously. Okay, so let's move on to our next theorem. Okay, let there be a transformation T from Rn to Rn, which means our transformation matrix is going to be n by n. Remember, this is the number of rows. This will be the number of columns. Okay, and let this transformation be linear and be given by this transformation matrix A, right? So T of x is the same as A times some vector x. Then the determinant of A, this transformation matrix measures the extent of volume or area distorted by my transformation. Remember, when you go way back to linear transformations in 3.1, we said that our transformations transform our vectors. They stretch our vectors in some way. They rotate them, they stretch them, they compress them, right? That's what a transformation does. So our transformation changes the matrices, and if we have a unit square, it changes and distorts the unit square by some amount. So what the determinant does is it's a measurement of the extent of distortion. Okay, it's very important actually. We'll talk later on in chapter 4.4 about another sort of distortion, but instead of distorting our vectors, we're going to distort the manner in which we measure our vectors. So it's a little bit different, but closely related to transformations. Okay. If D is the region that I'm looking at, for many of what we're doing, this was the unit square. Okay, and it has a finite volume in Rn. Then the area of the transformation of D is equal to the absolute value of the determinant of the transformation matrix times that original area of D. And if we're already in 3D, okay, 3 dimensions, then the volume of this transformation of our 3x3 area, this volume region that we have, is the determinant of A times the original volume of D before the transformation. So this is the area or volume after the transformation, and this is how we calculate it. Here the area of D or volume of D is before the transformation. So our area or volume gets distorted by a scalar multiple, because remember, that's what a scalar multiple is. The determinant of A is a scalar value. It's a single value, right? So the area gets transformed to a scalar multiple amount, or the volume, the original volume under the transformation, gets scaled by a real value amount. So let's look at an example, okay? Find a linear transformation T that gives a 1-to-1 correspondence between the unit circle, not the unit square, right? The unit circle and the ellipse that is provided below. So we have the unit circle. It's a circle with radius 1, centered at the origin. And what I want to do is I want to transform this circle into this ellipse. So let's talk about this. I'm going to write it all out for you guys, but let's look at this. How would I transform this circle into this ellipse? If this was a piece of clay that I had, how could I mold this to look like this? Well, first I would have to stretch it out from side to side and up and down, because this is 1, okay? So I would stretch it by 7 and this by 4, and then I would take that stretched oblong football that I have this way and I would rotate it 120 degrees, okay? So notice that the order that I do this matters, because if I were to rotate this 120 degrees first and then stretch it out in X by 7 and then by Y by 4, I would not have the same shape, okay? I would have rotated this to this position, but then I still would have pulled this out long ways, and I would have pulled this up long ways also by 4, right? So I would not end up with this rotated ellipse. I would have a standard ellipse with its major axis along X and its minor axis along Y. It would not be a rotated ellipse like this, okay? So the order that I apply these things matter, okay? So just think about that for a second to preface this. The general form for anything inside of the unit vector, the unit circle, I'm sorry, are the set of points x1 and x2 such that if I square x1 and I square x2 and I add them together, it has to be less than 1 or at most equal to 1. Okay, that's how we draw a circle, right? X squared plus y squared equals 1 is a circle with a radius of 1. Okay, here we don't have x and y, we do x1s, x2s, x3s, etc. Okay, our circle is not just the boundary, it's everything within the boundary. So I need to be less than or equal to 1. I cannot just strictly be equal to 1, because then I would only be the values along the edge of the circle and not the stuff that lies within it. Okay, this, for all intents and purposes, is an ellipse that has a major axis of 7 and a minor axis of 4, and of course it's then been rotated. But if we were to unrotate it, right, this would come out along X a distance of 7. So if you remember how ellipses are, it's your x1 squared. If this is the x1 axis, right? So this would be x squared over, and then the square of the distance you're stretching it along the minor. So this would be x squared over 49 plus x, or y squared over 16 is less than or equal to 1. That's how an ellipse is formed. So it'll be the same thing, but not x and y. It'll be x1 and x2. Okay, so x1 over 7 squared, or x1 squared over 49 plus x2 squared over 16 less than or equal to 1. However, here it's fine to just write it as the whole thing being squared, right? So that's how you're doing your stretches here. Okay, you're really just taking the unit circle and you're stretching it around. We're also rotating it. Okay, so to create our ellipse, the unit circle is expanded on the x1 axis, expanded on the x2 axis, and it is rotated 120 degrees. We have to do all of those things. So that's how we're going to build our transformation. Our one-to-one transformation should be a composition of singular transformations in the proper order. Okay, so a composition of transformations. So remember, when you compose two functions together, if I had a function f and a function g, f of g does not necessarily equal g of f. It does matter which function I plug into which one. It's the same thing for linear transformations. If I have t1 and t2, right, and I'm trying to find the linear transformation matrix that takes me straight from, you know, my domain to my end range, okay, the order in which I multiply those two t1 and t2s together to get that transition matrix, that transformation matrix, I'm sorry, matters, right? So I have to make sure I'm doing this in the right order. As I said before, if I do this in the wrong order, I'm just going to end up with a regular ellipse that has not been rotated. Okay, so the rotation has to be the last thing that I use. So my transformation, where I'm plugging in any two entry, any vector of, you know, in R2, the last thing it's going to do is be rotated 120 degrees. And the first thing that I have to do is stretch it by a factor of 7 in the x direction and a factor of 4 in the y direction. So my transformation matrix will be the product of these two individual transformation matrix because it's a composition of transformations. Okay, so I have actual values for these, right? This is 120 degrees. Go back to your trig. If this is 120, then that means that this reference angle is 60, okay? Which means that this side is equivalent to 1/2 if this was 1, and then this would be square root 3 over 2. So we have actual values for these, right? So the cosine of 120 is in the negative direction. This cosine should be negative 1/2. This should be negative root 3 over 2. Positive root 3 over 2, negative 1 over 2, okay? Oops. All right, so my rotation matrix times my expansion matrix times any vector I decide to plug in order to stay within that unit circle. So this is my transformation, okay? I can multiply these together, and this is my transformation matrix that gives me from the unit circle into that transformed ellipse, okay? So this would be the one-to-one transformation matrix. Now we're going to take this a little bit further, and let's figure out what the area of this ellipse is. Okay, I know that the area of this is pi r squared. R is 1, so this is really just pi. Okay, so if I want to find the area of this, I am going to use this formula. So the area of my transformed region, is the determinant of A, absolute value, okay, because you can't have a negative area, that doesn't make sense, or a negative volume. So I'm going to find the determinant of my transformation matrix, and I'm going to multiply it times my original area of that unit circle in this case, okay? So, right, because remember, this grows the area of this by a single scalar factor. So if the area of the ellipse is the absolute value of the determinant of A times the area of U, so the determinant of A is going to be these two being multiplied minus these two being multiplied. So this is going to give me a positive 7 because the 2's are going to cancel. This is going to give me, here the 2's are going to cancel. Root 3 is going to give me a 3. So I'm going to have 7 minus a negative 21, right? 7 times 3. Okay. So these cancel. These two root 3's cancel the root. This 2 and this 2 cancels. So I end up with 7 plus 21, which is 28. Okay. So that's the determinant, and that's not the full area. That was just one of the pieces that I need. So the area of U is pi r squared, where r is just 1. So that's pi. So that means the area of my ellipse is 28 pi. Okay. And in fact, if you go back and if you've ever had to find the area of an ellipse, it's really just pi times your major axis times your minor axis. That's actually the formula for the area of an ellipse. So 7 times 4 is 28 times pi, which is exactly what we got here. Okay, so there you go. Those are some of the uses of the determinant and things that we can do with it, as well as cross product, which I did not add into this because it's not covered in our book in depth. But as you can see, I added several extra videos, and as I said before, cross product is important. It's very important in physics. We're not going to discuss it here more than we have already, but I did add some additional videos that you can watch at your leisure, especially if you're a physics or engineering major. It is very important. We might talk about it later on in this textbook. I don't really remember, but most likely when we get to projections, cross product might come out there because it's pretty important. Okay. But anyways, this is a relatively short video as well. Hope you enjoyed. See you guys on the next one.